So welcome to lecture number 10. That's the supplementary part of the section on work and energy that we discussed a couple of days ago. So today what we'll do is we will solve some problems so that we get an understanding of how to apply these ideas and particularly when to apply these ideas so that they become effective. So we'll just do a quick recap of what we had discussed in work and energy. So we talked about the work energy theorem and some cases where we can apply this theorem more effectively. So ultimately what we had got was that the net work done on a system is equal to the change in its kinetic energy. So work can be done due to internal and external forces. So the internal forces again can be either conservative or non-conservative. So what we do is we only include the effect of non-conservative forces on the left hand side, and the conservative forces are considered as potential energy. So we will be using this form of the work energy theorem whenever we need this. So let's remember that this work energy theorem has been obtained from Newton's second law. So this is not the law of conservation of energy applied in a very general sense. Okay. Although that is a separate law in itself, the law of conservation of energy, but that includes other contribution as well. But we only have the mechanical part of this conservation of energy. So this is directly obtained from Newton's second law. And this becomes useful in certain situations. So we have situations where sometimes the path is known because the object is moving in a constrained sense. So we discussed in the beginning that what is the use of having this work energy theorem if we need the force as a function of its position, because if the position of the particle is known with time, then most probably a lot is known about the motion of the particle. But sometimes the particle moves in a groove or a constrained path. So in that case this becomes particularly useful because the path is known for a reason that it is constrained to move in a given path, but its velocity may not be known as a function of the position in the path. Okay, the other interesting thing is that whenever you want to constrain a particle, let's say in a given path, so the particle can only move in this path, then the path for some reason will apply a constraining force. Otherwise the particle will have a tendency to go anywhere. So if the particle tries to leave the path applies a constraining force, and this we call it Fc, the constraining force. And this constraining force interestingly does not do any work in general, because this constraining force is perpendicular to the movement of the particle. So it will not change the velocity because of the work energy theorem. If there is no work done by this constraining force, then there is no energy change due to this constraining force. So this purely changes the direction of velocity vector and does not affect the magnitude of velocity vector. Right, so let's jump into solving some problems to understand how to apply this theorem. So we have a problem of a spring and a mass. So there's a mass m that is connected to a spring, and this rests on a frictionless surface. So what we do is we give some initial displacement let's say x naught, and then we leave the mass, and initially the mass was at the equilibrium position. So this position is the equilibrium position. So we have to find out what is the position x. It's a one dimensional problem as a function of t. So this is the aim of this or the what is asked of the problem. So the first approach would be to simply apply the Newton's second law. That's most intuitive. So let's do that. So Newton's second law. So we see, first we draw the free body diagram. So there is only one force that is acting on the mass, and that is the force due to the spring Fs, which is equal to minus kx. So x is the displacement here, and depending on because initially the mass was at equilibrium position, so we'll call x the elongation or the compression in the spring. So in this case, the way we have drawn things, it's an elongation, and similar. So if this is the direction of x, then F spring acts in the opposite sense because it's a restoring force. So and we apply Newton's second law. So we say that the force Fs acting on the spring, so that's minus kx, is equal to mass times the acceleration of the mass. So this is what we get. And this, since we have to solve for x as a function of t, that is what is asked from us, we will write this in the form of a second order ordinary differential equation and solve it. If you know how to solve it, this is not a very complicated problem. But let us say we do not know how to solve a second order ODE, and we will want to use the work and energy approach to solve this problem. So let's try it the work and energy way. So in the work energy theorem, let's try to use the generalized form that we just wrote. So the work due to non-conservative forces in this case is 0, because the only force acting is the conservative force of the spring, and there is no external force acting, so there is no work due to external forces. So we can simply apply the initial mechanical energy is equal to the final mechanical energy. It's up to us how we want to take the initial and final positions. So we will take the initial position as the position where the mass was at the maximum elongation. So x naught was the maximum elongation we gave to the mass, so half k times x naught squared, and at this, and we left it. So at the maximum elongation the velocity was 0. We will say this is 0 because v naught is equal to 0, and this should be equal to the final energy, and since we are taking the final position as some arbitrary position, so this will have some amount of elongation or compression, whatever that is, and some amount of kinetic energy. So from this we can write the velocity v right, and this can now, so we can write v as dx by dt, because we have to solve for x as a function of time. So we integrate this from 0 to t, and 0 was when we t equal to 0 was the position at the time when we left it at the maximum elongation. So this was at x naught to some general position x. Right. So let's now simplify the integral. Sine inverse 1 becomes pi by 2, and this is what we get. So from this we can write x as x naught times sine of pi by 2 plus square root k by m t, and sine of pi by 2 plus something is cos of that, so this becomes cos square root k by m times t. So this is x as a function of t, and that is what was asked from us. Usually we write this as cos omega t, where omega is square root k by m. So that's the angular frequency. It's a simple harmonic motion. The mass oscillates about the mean position. So this is what we have. So we can check, I mean this should satisfy our initial conditions that we had supplied. So let's check. At t equal to 0, cos 0 becomes 1, so this says x is equal to x naught, and that is exactly what we had supplied. So we had stretched the spring to an elongation of x naught and then left. So this agrees, and let's see the velocity at t equal to 0. So if I put t equal to 0 here, I get a 0, and that is exactly what was supplied. So we had left the mass at x equal to x naught, so the velocity at that position was 0, and then it started moving due to the force of spring. So it was much more comfortable to get this solution as compared to if we had to solve the second order differential equation. it's up to you. So this I just wanted to show that the work energy approach in some situations can be more comfortable as compared to using the full force approach. Right. So let's try to solve another problem, which in which actually the work energy theorem is makes life much more simpler. So this is the problem of an inverted pendulum. So we have a mass that is connected through a rod of length L. So this is a rod, let's say it's a massless rod, and the pendulum is released at phi naught angle. So our job is to find the velocity of the mass m at a general angle phi. So when the angle is when the mass is making an angle, well, the massless rod is making an angle phi with the vertical, we have to find what the mass is, and this what the velocity is, and in this case it's a vertical placement. So we have mg acting downwards. So in this case, if I was to draw the free body diagram of the mass at some general position phi, so what I'll see is that there is one force that is because of the force of Earth's gravity, and there's another force which is the tension force due to the connected rod that the rod is applying on the mass. So if I was to apply the force approach, I'll have to consider both the forces. But interestingly, in this case, if we use the work energy approach, we get rid of one of the forces because the force of tension is always acting perpendicular to the direction of motion. So this is for this situation. So we can see that the motion is such that this is the direction of motion, this is the direction of velocity, or we should say this is the tangential coordinate. So we will see that the work done, the displacement, that's right, displacement. So this is our dr vector direction. So this is perpendicular to t. So in our active force diagram, where we only draw forces which the forces that do work on this mass. So if I was to draw an active force diagram, then the only force acting on this mass will be mg. So that potentially would make the life easier. So let's apply the work energy theorem here. So we say that the work done because of this force, we will apply the form where we have the potential energy. So there is no non-conservative internal force, so there is no work done because of that, and there is no external force as well, external active force, so that becomes 0 as well. So we can say that the initial energy of the system is equal to the final energy of the system. So in this case the system is the mass without the rod, and we also consider earth into the system because we are talking about the potential energy due to gravity, but we don't write that every time because we don't expect the earth to move because of the mass. It's only the mass moving. The earth is almost stationary and does not move towards the mass. So initially the mass, so let's draw the figure again. So we have so it goes from phi naught to some general angle phi. Let's so it goes from some phi naught to phi. So the initial energy will have a potential energy component and a kinetic energy component, same for the final energy. So let's see what the initial potential energy is. So let's say that the initial potential energy was 0, that is when the mass was at this height, and the initial kinetic energy was also 0 because we had left the mass when it was stationary. Now for a general angle phi, the height has dropped, so the change, if you have taken the initial as 0, its energy has decreased, the potential energy becomes negative mgh, and this h is simply L times cos phi naught minus L cos phi. Okay, that's the change in the that's the value of h, and the final kinetic energy is simply half m v squared. So when we simplify this, that gives us the velocity v as this. So this is v as a function of phi. In case I had asked you how does v depend on time, so there is no information. No information on v as a function of time. But that's okay. If the aim was simply to get v as a function of the angle phi, then we are happy with this situation. Now what I'll suggest to you is to try this problem using the Newton's second law. and then you will appreciate the simplicity that the work energy theorem can bring to the problem if you try solving the same problem that you've done right now with the Newton's second law approach. Right, so let's work on one more problem. So this is a problem on work done by central force. So first let us define a central force. So let's say a particle is moving in a path which is denoted by this dashed line, and at some time it is at a position P. With a position vector r. So central force is a force that acts along r hat always. So we can see that F, which is a central force here, let's call it Fc, is denoted by some scalar function small f as a function of r times r hat. So in this case, the center of this motion is defined using O. So Fc, that is acting on the particle, will always act along r hat, that is the position vector that joins the particle P to the center O, and its magnitude will only be dependent on the distance from that center, that is the distance r. So this is how we define a central force. So the work done due to this central force, then work has to be dependent on a path. So let's say the particle goes from A to B. So work done in going from A to B along this dashed path as shown is the integral along this path. So it's a line integral denoted by this C from A to B of the central force F dot displacement dr. So this sign says that it is along a curve or a path that is defined, and this is called a line integral. And dr, we already know the displacement dr in the polar coordinates. Basically this is simply our velocity times dt. So this has a radial component, that is dr, that is the displacement, that is magnitude of the displacement times r hat plus r times d theta times theta. So we simply multiplied our velocity vector by dt, and the velocity vector here is given in terms of r and theta. So let's substitute this expression for dr into the work done. So we get the work done going from A to B So Fc was Fr times dr, so this simply becomes Fr times dr, and that's it along the path. Now what we see is that it really doesn't matter what the path is in this case, because we see that this is purely a function of r. It only depends it only depends on the initial r value and the final r value, that is the scalar r, that is the distance from the center O. There is no dependent on the path. If there was a dependence on path, then you would have a dependence on theta as well, and r and theta would be related through some relationship that will define the path. But here there is no dependence on the path. So now we can conclude that central forces are conservative in nature. Because the definition of conservative forces was that the work done by those forces is independent of the path taken. So therefore we can define a potential energy associated with it. So this was a problem to show that the central forces are conservative forces. Now that we've talked about conservative forces, let's talk about non-conservative forces as well. So let's solve a problem on non-conservative forces. So let's take a non-conservative force F, some expression. So there is no physical meaning for this force. It is simply a mathematical function given to understand how to calculate the work done through for non-conservative forces. This is not a physical force, it is just an example. So if I have to calculate the work done due to a given force, I'll have to tell what the path is. So let's define the path. So we label these points as O, A, B and C, and our path, we will try to find the work done due to the force F for two different paths. So one is path 1, that will denote like this, and the other one is path 2, that is a longer one. So this is path number 2. This is path 1. So let's work with path 1 first. So the work done in path number 1 is from O to A. So for path number 1, this is a straight line which is along the x-axis. So we can write our displacement dr. So this is our force, and the displacement dr can simply be written as dx along I hat, and force is a times xyi plus y squared j, and it goes from 0, 0 to 1, 0. So what we see is that this actually will become 0, because it will become xy times dx, and whatever the x expression is doesn't matter, because y is 0 for the whole path. So this becomes 0. This is for path number 1. Let's take path 2. So for path 2, let's write path 1 and path 2. So for path 2, the integral of f dot dr now involves 3 straight line moves, because that's how we define path number 2. So this becomes a straight integral from 0 comma 0 to 0 comma 1 of f dot dr. So f is the same, we'll write dr as in this case it's only in the y direction. There's no I hat for this vector dr, plus the second integral is along this line. So this becomes from 0 comma 1 to 1 comma 1 of f dot, and again dr in this case is along the I hat, and then the third one is from 1 comma 1 to 1 comma 0 of f dot, again it is only along the y direction. Now I have not taken a minus because that automatically gets taken care of depending on what limits we are putting. So we are just talking about the general direction in which the particle is moving. Okay. And now we simply have to write these, simplify the integrals. So if I put the expression for the force, this will give me let's use a bit more space. So for the first case we have y square dy integrated, so that is only a function of y, and y goes from 0 to 1, so that becomes y cube by 3 from 0 to 1, so that's 1 by 3. Next is f dot dx. So dx is xy, so we have x dx integrated, that becomes x squared by 2 times y. Now for the second line, this y is equal to 1, so there is no contribution from that, and we have 1 upon 2. And the last one is f dot dy, that becomes again y cube by 3 from 1 to 0, so that becomes a minus 1 by 3. So this becomes equal to half. Okay, so what we see is that depending on the path, the work done is different. So this is a non-conservative force, and this is how we evaluate line integrals depending on the path that is given to us. Okay, so this is just one example to show you how to use non-conservative forces when evaluating integrals. Right, so let's move on from here. Let's now solve a problem where the path is, it's a non-conservative force still, but the path is not as comfortable as straight line moves. So this is a problem that uses parametric evaluation of line integrals. See, if the force is conservative, then there is no point finding the work done along a path. You can choose the simplest path you can find between the 2 points and then evaluate the work done, because for conservative forces it only depends on initial and final position. So this is for non-conservative forces where the path actually matters. So the problem is we have a particle moving in a circular path. So from point O to point A, it moves in this semicircular path. The radius of the circle is capital R and the theta general angle is given as this theta. So we have to find the work done by whatever force is acting. I'll tell you what the force is along this path P, and this is a line integral, that is because it's on a given path. So we always put this C to denote it's a line integral as opposed to an integral from that is independent of path. And F here is the non-conservative force, is again just some hypothetical expression, no physical force as such, is given as this function. So we use the idea of parametric form because since it's moving in a path, the x and y coordinates of the particle P at any given position are dependent on each other, and the parameter that we can use to show the dependence is through angle theta. Theta is the single parameter because it's a single degree of freedom problem. So x becomes x coordinate of the particle, well, let's say here, this becomes, sorry, it's r sine theta, and y becomes so the way the problem is defined, it becomes capital R minus R cos theta. So from these we can calculate dx and dy. So dx becomes R cos theta d theta, and dy becomes R sin theta d theta. So let's evaluate the integral f dot dr over the path P. So dr becomes dx I hat plus dy j hat, and now we do not need to use the sign C because we already have taken into account the path. Now the only we'll also have to substitute for x and y. So I'll still keep C here because I have not substituted what x and y are. So for this given motion along a path, this becomes, so x is r sin theta, so we can actually take r to the 4 outside, and theta goes from 0 to pi radians. Okay, so this is now this integral is not a very difficult integral to solve. So this can easily be solved if you use some substitution. I think cos theta equal to some variable, let's say p. So I'll leave it to you to solve this integral, but what I wanted to show you was how to solve these line integrals for non-conservative forces using parametric forms. Right, so let's try another problem. So in this case, this is about potential energy. So we discussed that central forces are conservative forces. So how do we find a potential energy function corresponding to a central force? So let's solve a problem related to that. So potential energy of an inverse square force which is a special type of central force. So we discussed that central force is a force that is some scalar function of the distance r from the center times r hat. So this scalar function f can have different forms. So for this particular case where we talk about an inverse square force, this is of the form a upon r squared. So as the distance increases, the force decreases as 1 by r squared. Many kinds of forces are inverse square forces. For example, the gravitational force, it is an inverse square force. The other example is Coulomb force. It's also an inverse square force. So it's worth talking about these kind of forces. So by the definition of potential energy, we said that the change in potential energy is negative of the work done due to the force, internal force. So this becomes minus f dot dr along a given path, but this is a conservative force, so we don't need to define the path, we only need to define the initial position and the final position. So we are trying to find what u expression is. Now since we are talking about a general u as a function of r, so we will take the final potential energy at some displacement r or some distance r from the center minus the initial potential energy is something that will be known for a given position. So this integral we a few minutes ago we solved that as Ra to Rp, that's the distance of Fr dr. So for this particular case, sorry, there's a negative sign here. For this particular case, this is a upon r squared dr, that is for the inverse square force. I'm sorry, this is we're doing it from some position A to a general position R, okay, because that is what we have been using here. So this becomes 1 upon A upon R minus A upon RA. So we'll call ui as nothing but u at a known position RA. So this is our u as a function of r. Now remember that we are completely free to choose what u at given Ra is, because what matters is the difference in energy. The absolute value at a given point does not have any effect as long as we define a reference. So we would want to define the reference in such a way so that u at infinity, so when the particles are infinite distance away, this is 0, and it makes sense because when the particles are very far away so that they don't feel each other's force, then the energy is defined to be 0. So if we define it this way, then you put r equal to infinity, so we get u at infinity is equal to u at Ra plus a upon infinity, that becomes 0, and then minus a upon r a, and this was defined to be 0. So this says that u at Ra is equal to a upon Ra. So if we substitute that, we basically get the expression ur is equal to a upon r. So this is the expression for the potential energy for central force of the type of inverse squared force. Right, so another problem. So we'll solve two more problems today. So in this case, we have a hoop and there is a bead that moves over the hoop. And this is the vertical plane, so G is acting in this direction. So we have a bead that is moving over the hoop, and the bead is connected through a spring to this bottom position O. In this case, there is no friction on the hoop, so the bead moves on the hoop without friction. And you can also assume that the equilibrium length of the spring is 0. So whatever the distance of the bead from the center O is, that is considered to be the elongation in the spring. Approximately 0. Okay. So the bead is released from the top. This is top. So when I say released, that means at the top it did not have any speed, and we have to find the speed of the bead when it reaches the bottom position. So this problem becomes extremely easy if you apply the work energy theorem. Because the forces acting on the bead are the force of gravity and the force due to the spring, and both are conservative forces. So we can use the idea of work energy theorem with only conservative forces. That means the energy initial becomes equal to the energy final. Take the whole system of the bead, the hoop, and the spring and everything. So of course, I mean, we take the earth in the system as well, because we're talking about internal energy. So we have to take the system that includes both the particles, but the earth does not move. It's only the bead that moves. So we can use, neglect the motion of earth. If you're talking about two large bodies like two planets, then we'll have to consider both of them if they're of equal masses. Anyway, so this can be used because work due to non-conservative internal force and work due to external force both are 0. So if I apply this, then we get the position, so the velocity of the speed of the bead when it reaches the bottom position. So that is VO as this expression. All right. So we'll now solve one last problem. So for that, I need to show you the problem. So here's the problem. So we have a plunger. Now please ignore the British units here. So let's keep it more general. So this is a mass m of a plunger. So this plunger is released from rest when theta is 0. So this is the angle theta that these rods make with the horizontal. So when theta was 0, we had released the plunger from rest, and because of its mass m, it will have a tendency to fall. There's a spring, there are two springs, each having a stiffness k. Again, let's not worry about the value. What happens is the spring was initially uncompressed, but when the mass falls, when the theta angle increases further from 0, the spring will start compressing. Of course, the rod will rotate, but because the rod length is constant, this length in total is constant. So since a larger length is now taken by the rod that does not have the spring in it, so this spring gets compressed as theta increases. Okay, that is what is said by the statement. The links are free to slide to their pivoted collars and compress their springs. So what we have to calculate is the velocity v of the plunger. So the plunger is falling down. We have to calculate what the velocity v is when the plunger has moved such that theta is equal to 30 degree. So at theta equal to 30 degree, we have to find the velocity of the plunger. Again, the problem's quite straightforward if we use the work energy approach. So let's do that. So in this case, when we use the work energy approach, there is we can use this expression of initial mechanical energy is equal to final mechanical energy, because the work due to external forces and non-conservative forces are both 0. Okay, so this says that initial potential energy plus initial kinetic energy is equal to final potential energy plus final kinetic energy. So we will take the initial conditions as those conditions where the angle theta was 0 and final is some arbitrary value. Well, actually this is at theta equal to 30 degrees, but we can write in a general sense. So we can define the initial mass. So let's call this distance as d. So we can write tan theta is equal to the height h of the mass. That's the mass has fallen down through height h, and that's h upon d. So we can write the value h as d tan theta. So d is given to us, that's because of the geometry, and theta is the angle. So we have written an unknown h purely in the form of d and theta. So this allows us to write the potential energy due to gravity. So we will call it u due to mg, just g, u due to gravity. So that is mg, and the h in this case is negative because we have defined the 0 gravitational potential energy at theta equal to 0. So this becomes mg times minus h, which is minus d tan theta. So that's the final expression for the gravitational potential energy. So next we have to find the final expression for the potential energy due to spring. The spring is half times k times the compression or the elongation of a square of that, and since we have two of these, so the energy is double. So we'll say twice of half k and let's see what the elongation is, what the compression of one particular spring is. So initially the length of the rod is fixed, that is L, and initially when theta was 0, that is equilibrium position. So the length of the spring plus d was equal to the total length of the rod. So when theta is some general theta, then whatever the length of spring at some theta is, plus, now this time we are talking about this length. So this length, let's call it P, that will be again equal to L, and this L is nothing but Ls plus D. So we are trying to find Ls theta. In fact, we are trying to find the change, so we can write Ls theta minus Ls. So that's the that will be a negative value because the spring has compressed. So the length of the spring at theta angle minus the length of the spring at theta equal to 0 will be something negative, but that's okay. We want a square of that, and that becomes D minus P. And this P, again we can see that P is larger than D because the angle theta has a positive value now. So this P times cos theta is equal to D, so it becomes D by cos theta. And that is the delta L spring. So delta L spring becomes D into 1 minus 1 upon cos theta, the square of that. So the initial kinetic energy and potential energy both are 0, and the final potential energy is U gravity plus U spring, and then you have the final kinetic energy, which is half times m times v squared. So now it's just a matter of substituting these expressions and solving it for the velocity v. So that should be simple. So we will stop here now, and this was a supplementary session to our lecture number 10, that was the lecture on work and energy ideas. So I hope this was helpful, and we will record more such sessions that will involve problem solving for the different topics that we have discussed in this course. Thank you.